first talk of the session will be given by Kuan Cheng on relaxed locally decodable codes.
Thanks for the introduction. Yeah, I'm Kuan Cheng from Peking University. This talk is based on a joint work with Alexandra Block, Jeremiah Blocky, Lena Grigorescu, Xinli Yuzheng, and Minshen Zhu. So I'm going to first introduce the background of our problems, and then exhibit our results, and then show our technical highlights, and then show some open problems. Introduction. So I will first introduce the definition of insertion-deletion distance. So I guess we are very familiar with Hamming distance. Given two strings, x and y, for example, they are binary strings, the Hamming distance is defined to be the minimum number of substitutions transforming x to y. Insertion-deletion distance, on the other hand, it is defined to be the minimum number of insertions and deletions transforming x to y. Notice that this kind of insertion and deletions can cause substrings to shift, which is harder to handle. Error correcting code. So I guess we are more familiar with this definition. So we can imagine, we can define a code to be a mapping, which is the encoding function, mapping a message set to a code word set. And what we want is that we hope that the distance between any pair of code words is somewhat large. So the distance is defined to be the minimum of all pair of minimum of the distance of all the pairs. So here we mainly consider distance measure to be insertion-deletion distance and Hamming distance. Local decoding. So given a code word y, now imagine that there are eta fraction of errors happen on y. And then we get a corrupt version y prime. And the local decoder want to compute a message bit xi on input y prime and an index I in n. And here, for local decoding, it's called local because we only allow this decoder to query Q symbols. Usually it's a random query. So specifically, we require that with probability at least half plus epsilon, the decoder should output the correct bit xi. Previous results about locally decodable codes, I think this is there are many famous results in this research line. So especially for Q equal to 2, Krendis and Dwarf 04 and Ben Arroyo Rigov Dwarf 08 showed a strong exponential lower bound. This lower bound shows that the code word length should be at least exponential in omega of n. And for Q, which is at least 3, so for the upper bound, Yakhani 08 and DGY 11 and Afremenko 12 show that m can be exponential of n to small o of 1, which is sub-exponential length. For the lower bound, Woodruff 07 showed that m has to be at least omega of n to a constant which is slightly larger than 1 than over this log n. So notice that there is a big gap between upper bound and lower bound for Q, which is at least 3. What's more, recently, very recently, Arabian et al. 23 showed that for the Q equal to 3 case, there is a cubic lower bound. So for the in-style LDC, we also have a lower bound. So Blocky et al. 22 showed that for Q equal to 2, for the linear or affine case, the message length has to be a constant. And for the general case, m is exponential in n. For Q, which is at least 3, they show that m has to be exponential in omega of n to 1 over 2q minus 4, which is a sub-exponential lower bound. Relaxed local decoding. So this is a relaxed version of local decoding. So the definition is similar, but however, there are some difference in the decoder. Again, we have a code word y and have some errors on y. For this cropped version y prime, we require that the decoder on input y prime and the index I in n should either output xi or abort with a constant probability alpha. And again, we should require the decoder to query Q symbols following some distributions. Okay, so here we can see the exact definition, which is similar to the graph in the previous page. Especially there's a little difference. So this definition is a stronger version, which is a strong ILDC definition. So the difference is only about the third property. So, so the third property says that if the error fraction is at most eta, then there is a set I, which is a subset of n. So this I has to have size at least rho n, such that for every index in I, the decoder can correctly output xi with probability at least alpha. This means that there is a subset such that we can, the decoder do not have to abort. It can output xi correctly. So yeah, if with the third property, then it's called strong. But if without the third property, it's called weak. Notice that in the original paper introducing the definition of RLDC, BGH plus 0.6, they showed that one can use property 1 and property 2 plus some average case smoothness property to give a strong RLDC. So related literature about this topic. So originally motivated by the large gap in the constant query LDC, Ben Sesson, Godric, Hasha, Sudan, and Vedan 06 introduced ILDC for Hamming distance. And they construct strong ILDCs with constant number of queries, and also the code word length is slightly superlinear, which is n to 1 plus big O, 1 over square root of Q. And then Asadi and Shinka improve the bounds to m equal to n to 1 plus big O, 1 over Q. Then Gore and Lachish 21st show that for every Q, which is at least 2, there's a lower bound. So for every weak Q query ILDC, it must have length m equal to n to 1 plus 1 over big O Q squared for non-adaptive decoders. Then DGL 21st further extends this result to the adaptive case. The parameter is only has a slight difference, but yeah, it's almost similar. And what's more, GL 21st conjectured that for Q equal to 2, there is an exponential lower bound, matching the lower bound for the standard ILDC case. Also, some recent work by Cohen and Yakovi 22 improved the query complexity for asymptotically good ILDC. And also, this year by Kumar and Mon, they construct ILDC using LTCs. The result has a polylog number of queries, and the construction is close to the GV bound. So our results. So we have 3 results. The first result is about the Hamming case, weak ILDC. We have a lower bound. The lower bound is saying that if C is a weak adaptive to query eta half plus epsilon ILDC, then we should have an exponential lower bound, which is m equal to 2 to omega of n. This partially answered the question mentioned by GL 21st. Partially means that if you notice the detail that in our definition, we require the ILDC to have perfect completance, which means that if there's no error, then the decoder should output the correct message read. We know most constructions, almost all the constructions actually have this property. Okay, so our second result is about insertion deletion codes. So if C is a non-adaptive, strong in-style RLDC, then we again can have a exponential lower bound. So our result is saying that for every Q which is at least 2, there is a constant C1 such that m is equal to exponential in C1 times n to some omega of beta square over Q. And we have a third result, which is a construction. So for the weak non-adaptive install RLDC case, we have a construction. So our construction has code word length big O n to 1 plus gamma. This is for constant query Q. Okay, next let's see some technical highlights. So first, let's see some techniques about the exponential lower bound for Hamming case. So our general idea is saying that we found that one can transform any two-query weak Hamming RLDC into a standard two-query Hamming LDC. So our result for the, holds for the adaptive case, but for simplicity of exhibition, we mainly talk about the non-adaptive case here. So the general idea is similar between the two cases. So we want to do the transformation, and we want to make sure that the parameters do not change too much. So if originally we have a two-query RLDC with message length n, then we hope to have a two-query standard LDC with message length omega of n. And also the fraction of errors, if originally is eta, then we also want the, after the transformation, the result LDC can resist some eta over 2 fraction of errors. So then if we can do the transformation, then we can use the lower bound for the standard two-query LDC. Then let's see some detail about this transformation. We start from the relaxed local decoder. So consider one decoding function, fi sub gk. So we know this is a two-query case. So for this message I, this function is querying position g and k. So we can write down the truth table of this function. It's a very small scale truth table because we only have 2 inputs. We have the following observations about the truth table. So we can consider several situations according to the number of abort in the truth table. So notice that if there are 0 number of abort, then this is very good for us because the decoding function do not abort, then it is a standard local decoding function. If there's only 1 abort, notice that for this case, we can have some fixing properties. Specifically, one can say that yg can be fixed to be a constant by setting either xi equal to 0 or xi equal to 1. And and for yk, we also have the similar observation. If there are 2 or 3 aborts, we again can have this property. So if there are 4 aborts, this is not possible since we require perfect completeness, which means that if there are no errors which will output the correct message bit, we cannot output abort. So in summary, if there are 0 abort, then this is good. It's a standard local decoding function. If there are any abort, for example, 1 abort or 2 abort or 3, then we can have this fixing property. Okay, then let's introduce some more definitions to do the further argument. So we use SI to denote the set of all indices G such that YG is fixable by XI. And we use TG to denote the set of all indices I such that YG is fixable by XI. Okay, so to do the transformation, let's analyze the query structure. So we want to get a standard local decoder from a relaxed local decoder. So let's look at this query structure. So a query pair GK, we can see that it can fall into one of the following 3 cases. So first, both GK are in SI. And second, both GK are out of SI. Recall that SI is defined to be the set such that it includes all the YG which can be fixable by XI. So notice that for the second case, this means that there should be no abort in FGK. And for the third case, one of them is in SI, the other one is out of SI. This is not possible according to our previous observations. Okay, so we only have two cases. And then let's consider the conditional success probability. So consider two events according to the positions of GK. One is both GK are in SI, the second one is they are out of SI. Then let's denote the event E1 to be that the first situation happens, and E2 to correspond to the second situation. So then we can write down the decoding success probability in a conditional way. So just use consider the conditional probability according to the two events. Also notice that we have the following observation, that if the size of SI is at most some constant fraction times m, then only using queries outside of SI should give us a standard LDC. Let's see why this is true. So consider two code words, y and y prime. So y corresponds to the message x, y prime corresponds to the message x prime. And we make sure that the s bit of them is different. So by perfect completeness, the decoding of the decoder on I and y prime should output xi prime. Then we can, in the analysis, we can construct a hybrid string y tilde, such as the blue part is similar to the corresponding part of y prime, and the white part corresponds to the corresponding part in y. So this can be viewed as a crafted version of y. So we can notice that if we run the decoding on this y tilde, the probability that condition on E1, that the decoder can output xi or abort, this probability should be 0, because GK lie in SI. So this means if we go back to look at this conditional probability, because the first part has to be 0, so the overall success probability should be at least half plus epsilon, so the second part should be large. So one can deduce that the second part, the conditional probability condition on E2 should be at least half plus epsilon. So if we have the case, then one can notice that we can transform this relaxed decoder to a standard decoder. So the only thing we need to show that the size of SI has to be bounded. However, it turns out this is not true for an arbitrary RLDC. But one can notice that it still suffices if one can prove that SI can be upper bounded for a constant fraction of message bits. But it turns out this is, again, not true for general RLDC. So we need to slightly modify the construction. So our idea is to use a random restriction and use a double counting-like argument to make it work. So it's a simple random restriction. We just do random restriction on the message. And here in the analysis, we should use the notion TG. So the idea is that we can notice that by the definition, summation of SI is equal to the summation of TG. I mean, in size. So if after a random restriction that we can somehow show that for most G, TG has a good upper bound, then somewhat we can use a double counting argument to show that for most I, SI should have a good upper bound. So that's the idea. So we can slightly dig into the details. So, for example, there are some bad examples. So if TG is equal to n for most G, this is a bad case. That for each G, YG is equal to the end of some message bit, the end of all message bits. However, one can notice that for these cases, if the corresponding TG has a large size, and if we do a random restriction, then with high probability, the corresponding symbol should be fixed. The YG should be fixed. So that's a general idea. So for this large TG with high probability, the corresponding YG should be fixed. So that's the general idea. So we can use random restrictions to reduce the size of TG. Okay, so after this random restriction, some code word bits are fixed. So we just remove these fixed bits and get a new code. So for this code, we can use a double counting argument to argue that for most I, the size of SI can be upper bounded. So that's a general idea. Okay, so we still have some time. So for the lower bound for strong in-style RLDC, for the Q equal to 2 case, we can actually use the same idea. Our reduction, our transformation also works for the in-style case. We can transform RLDC to LDC. And then by using BCG plus 22, which is a strong lower bound for the in-style LDC, especially for the linear and fun case, the message length has to be a constant. And for constant Q, if we start from Q delta half plus beta rho strong in-style RLDC, we can show that a transformation can also be established. We mean that we can still transform this kind of RLDC to a standard LDC. The general idea here is simple. So we can first use some repeatings on the decoding to enlarge the success probability, and we use the strongness to directly argue that we can do a small modification on the decoding to get a good decoder, which is the standard decoder. And again, we can use BCG plus 22 as a black box, because after we have this LDC, we can use a lower bound for the LDC. The construction of the weak in-style RLDC. So for this part, we basically use a concatenation technique. So we start with the outer code, which is a non-adaptive, weak, relaxed Hamming LDC given by the original paper. And then we set up the inner code to be a linear in-style code with heavy weight, and which is asymptotically good. Then we insert some zeros in between the blocks, and we can show that this indeed can work. Okay, some open problems. I think the most intriguing problems is the first one. So our two-query RLDC has, the lower bound has an exponential length, but there are constant query RLDC with polynomial length. So there has to be a big switch. So the question is, for which Q there is a maybe sub-exponential lower bound, but for Q plus 1, there is a polynomial construction. And also, a related question is that whether we can generalize our lower bound to the query equal to 3 or 4 or 5 case. The second open question is, can we remove the requirement of perfect completeness? I don't see any reason that we can't do that, but I also don't see the technique to do that. The third question is that whether we can construct a strong in-style RLDC. Okay, thanks. Any questions?
Questions for Kuan Cheng? If not, let's thank Kuan Cheng again.
Thanks.